So in the third part of our video, we come now to a real preparative separation, and we will set up something which you will use as the preparative separation of a compound of interest. Everything we have done so far was a quite easy system. So we had a column, and you know now what's in this column. We had a mobile phase, and this mobile phase was pumped through a pump, through the column, and here we collected our compound. But we never changed the composition of our mobile phase. So over time, the composition of our mobile phase was always the same. This is a situation which we call isocratic. But it's not the widely used method. It's a very easy method because you only have one solvent. But in most of the cases, you need more than just this one solvent. In the easiest way to use more than one solvent, we have a second one, this blue one here. And after a certain time, we switch, we introduce the second. And what we get then is a step. First solvent, second solvent. This is what we call step gradient. What is different in the second solvent, that can be different parameters. It can be a different pH. It can be a different salt concentration. It can be a difference in percent of organic modifier. Typically, what is used is something which gives you an adjusted desorption of your compounds of interest. Beside the isocratic way and the step gradient, there is another way to do this change in mobile phase, which is a linear increase in the concentration, the pH, whatever. So this is called a linear gradient. Once again, this is called the step gradient. This is the linear gradient. The linear gradient is often used to do a screening. So with the linear gradient, we have the whole area, a very wide area, and we see with the screening gradient where our peaks of interest elude. And now we take this system and bring it to a real chromatographic system. So we start in our column with an equilibrated column, an equilibrated system. So we have the initial conditions of our mobile phase, which is there in the whole column system. At a certain point, we do an injection. You will not recognize any change in the baseline of our UV system because what is injected is bound to our column. Then we might change our mobile phase composition. So we take a first increase in one of the parameters and we have a wash step. The wash step is used to get rid of loosely bound compounds which are in our column and which bound more loosely than our compound of interest. The next step is we increase once again the elution efficiency of our mobile phase. And now we elute our compound of interest. So this is our material we would like to collect. In most of the cases, we still have material on the column which is strongly bound and which we would like to get rid of. So now we increase again the elution power of our mobile phase. And with that, we get rid of materials which is strongly bound. In case of biological systems, we often increase then again the elution power, but now by introducing caustic, so sodium hydroxide, for example. And with that, we clean out every material which might foul our column. You will not see a lot of material coming off here. And typically this is something which is using, let's say, 0.1 molar sodium hydroxide. After we have finished that step, we have to make sure that our column is again prepared for the next injection. So we have to go back to our initial mobile phase composition and re-equilibrate our column. And now we are ready to inject the next portion of our material to be separated. And everything from here to the re-equilibration here is what we call the cycle time. As you can imagine, the cycle time should be as short as possible, because the cycle time is determining our productivity. Productivity is the number of injections you can do per given time period. Might be 1 hour, might be a shift of 8 hours, might be 24 hours, multiplied by the amount which is injected into the column. So, last point to consider is, what is the optimum amount to be injected into our column? And for that, we have to have a look into how can we determine the optimum amount which we can inject in our column. And for that, we have to have a look to the adsorption isotherm. The adsorption isotherm is a simple equation where we have the concentration of our compound of interest in the mobile phase and the concentration on the stationary phase. If we have low concentrations in the mobile phase, everything which is in the mobile phase is adsorbed on the stationary phase, and we have a linear increase here in what is bound to the stationary phase. This is called the linear range of the adsorption isotherm. And this is the area where all the analytical chromatography has to work, because otherwise you don't have a linear relationship and you cannot quantify what is in your mixture to be separated. But we in preparative chromatography, we want to work up here. Maximum loading on our column. And when we do that, so when we determine the loading at different concentrations of mobile phase, what we will see is that this flattens out. So we have a certain maximum capacity of our material to be separated. And if we do that in a static way, so if we do that in a batch format, in an Eppendorf, we determine what is called the static binding capacity. Concentration of our target compound in the mobile phase, and we determine what is the capacity in the stationary phase. The higher the static binding capacity, the better a chromatographic resin is usable for your separation task. But it's not static that we are separating. So what we would like to do is we would like to separate in a dynamic fashion. We are pumping our mobile phase through the column. And for that, we have to determine the dynamic binding capacity. And for that, we take our maximum concentration we have determined with the static binding capacity, pump it through the column. First of all, nothing happens, but then we have a breakthrough of our compound of interest. And it flattens out here, it reaches a maximum, which should be pretty equal to the static binding capacity. What is typically taken as a measure is, where is this dynamic binding capacity reaching 10% of the maximum capacity? This is called dynamic binding capacity at 10%. And because we don't want to lose this material, which is leaving the column unretained and which we cannot collect in high purity. We have a certain safety margin, so we don't use the DBC10, but we use, let's say, only 70% of the DBC10. And now you know how much you can inject in your system. You can inject this amount of mobile phase, milliliter, times the concentration in your mobile phase. So for example, if you have a titer of 5 grams per liter and you can inject 100 milliliter, this is the amount you use for the injection in our preparative separation. And that's the whole magic of preparative chromatography. Once you have determined all that, once you have found your optimum selectivity, once you have minimized your cycle time, you can run that in an automated fashion in columns up to 2 meter diameter, 24 hours a day, and you have your production process. And if you're developing these production processes, good luck to achieve the best productivity you can imagine. Thanks for listening.